Look up into the night sky on a clear, dark evening, far from the city lights, and you might just see a faint, hazy patch of cosmic light, a distant galaxy, home to billions of stars, swirling in the vast emptiness of space. But among these countless islands of stars, there is one that stands apart, not just for its beauty, but for its mysteries, the majestic NGC 1300 galaxy. Imagine a colossal barred spiral over 100,000 light-years across, with arms swirling like a celestial whirlpool, glittering with star clusters, nebulae, and secrets we are only beginning to uncover. What cosmic wonders lie hidden within this faraway realm? What strange, almost unbelievable phenomena are waiting to be discovered in the depths of this galactic giant? This is not just another pretty picture from a telescope. Behind that breathtaking image of NGC 1300 are stories of bizarre, unexplained occurrences that challenge everything we think we know about the universe. From stars that vanish without a trace to regions of space where the laws of physics seem to break down, this galaxy is a treasure chest of cosmic oddities. And that's exactly what we're setting out to explore together today. We're going on a journey not just through space, but through wonder, through curiosity, through the very edges of human understanding. In this video, we'll uncover 30 of the most strange, captivating, and truly mysterious phenomena ever observed within NGC 1300. Each one is a piece of a puzzle that stretches across time and space, inviting us to question, to imagine, and to marvel at just how little we truly know about the cosmos. So settle in, open your mind, and get ready to explore the unknown. Because what we're about to discover might just change the way you see the night sky forever. Our journey into the strange and unknown begins not at the galaxy's edge, but right at its very heart. When astronomers first trained their most powerful instruments on the core of NGC 1300, they expected to see the clear, powerful signature of a supermassive black hole, the gravitational anchor common to most large galaxies. Instead, they found a void, a profound nothingness. The central region, which should be a maelstrom of intense gravity and energetic radiation, is eerily quiet. This absence itself is a phenomenon so baffling it forces us to reconsider one of the most fundamental tenets of modern astronomy. Where a gravitational monster weighing millions of suns should reside, there is only a strange, unsettling silence. This isn't just a missing object, it's a direct challenge to our models of how galaxies form and evolve. One leading theory suggests the black hole could be in a dormant, quiescent state, a sleeping giant that has consumed all the immediate fuel and simply shut off. Another, far more radical idea is that we are looking at the aftermath of a truly colossal event. A gravitational wave recoiled so violent it physically ejected the black hole from the center of the galaxy, hurling it out into the intergalactic void. If true, this would mean we are witnessing the ghost of a galactic core, a remnant of a cosmic catastrophe on an almost unimaginable scale. This central mystery sets the tone for everything that follows in NGC 1300. A place where the expected rules of the cosmos simply don't seem to apply. Leaving the eerie silence of the galactic core, our journey takes us out into one of the galaxy's magnificent spiral arms. Here, amidst the brilliant clouds of star-forming gas, telescopes have captured something that shouldn't be there: sudden, violent flashes of the highest energy light in the universe. These are gamma-ray bursts, cosmic explosions so powerful they can briefly outshine an entire galaxy. But the ones in NGC 1300 are different. They are ghostly, unexplained, and they break all the rules. Typically, a gamma-ray burst is the death scream of a massive star collapsing into a black hole or the merger of two incredibly dense neutron stars. These events have a clear origin point and a predictable, if spectacular, fade pattern. The bursts in NGC 1300, however, emerge from what appears to be pure, empty space, vast voids between star systems where there is nothing to trigger such a cataclysm. Even stranger is their timing. Instead of a single, random eruption, these bursts arrive in a distinct, almost rhythmic pattern, a series of pulses with quiet periods in between that suggest something other than a simple stellar explosion. The energy signature they leave behind is their most baffling quality. It doesn't match the fingerprint of any known cosmic event. It's as if the universe itself is flickering in these spots for reasons we cannot yet comprehend. This has led astronomers to propose sources that sound like they belong in science fiction. One compelling idea points to primordial black holes. These aren't the black holes formed from dead stars. They are hypothetical remnants from the very first moments after the Big Bang, tiny and elusive. A swarm of these ancient objects passing through the galaxy could collide and evaporate in a flash of energy, creating these bizarre, patterned bursts without leaving any visible trace behind. An even more exotic possibility involves dark matter. This mysterious substance makes up most of the mass in the universe, but we have never directly seen it. What if dense knots of dark matter are concentrated in these regions of NGC 1300? Could the mutual annihilation of dark matter particles be generating these immense bursts of energy? If so, we might be looking at the first ever indirect detection of dark matter's hidden interactions, a clue to the greatest mystery in modern physics playing out in the arms of a distant galaxy. These ghostly flashes are more than just random explosions. They are potential messengers, hinting at a whole new layer of reality operating just beyond our current understanding. The peculiarities of NGC 1300 are not confined to its spiral arms or its silent heart. Deep within that same galactic core, another discovery has left astronomers utterly perplexed. It appears the central supermassive black hole, or what remains of it, is not sitting still. Instead, it seems to be moving. This isn't a simple, smooth orbit. The motion detected is a strange, irregular wobble, like a spinning top beginning to lose its balance. The detection of this movement is a feat of extreme precision. By tracking the orbits and velocities of stars clustered tightly around the galactic center over many years, scientists can map the immense gravitational field that dictates their motion. The paths of these stars revealed a gravitational source that is not perfectly stationary. It is shifting, oscillating in a way that a supermassive black hole, an object with the mass of millions of suns, simply should not be able to do. The implications of a wobbling black hole are profound and challenge the bedrock of black hole physics. An object of such unimaginable mass possesses immense inertia. It should be the most stable, unmovable anchor in the entire galaxy. For it to be seen wobbling suggests it is being influenced by a force of almost equal magnitude. One compelling explanation points to a recent gargantuan meal. If the black hole consumed another large black hole or an incredibly dense star cluster, the transfer of momentum from the infalling object could have given the central giant a literal kick, setting it into this strange motion. However, the wobble appears too sustained for a single event, suggesting an ongoing disturbance. This leads to an even more thrilling possibility, the presence of a second, unseen black hole. We could be looking at a binary system where two supermassive black holes are locked in a slow, gravitational dance within the core. The wobble we detect would be the visible signature of their orbital motion around each other. The potential existence of such a binary pair opens up a new chapter in cosmic predictions. Their eventual merger, which could take millions of years, would unleash the most powerful gravitational wave event in that part of the universe, rippling through the very fabric of spacetime itself. This dancing anomaly is more than just a curiosity. It is a direct window into the violent, dynamic processes that shape galactic centers, offering us a front-row seat to a cosmic ballet of unimaginable scale and power. Moving outward from the galaxy's dynamic core, we encounter a phenomenon that challenges not just our understanding of space, but the very nature of time itself. Nestled within the spiral arms of NGC 1300 are several enigmatic nebulae, vast clouds of gas and dust where the normal rules of light and observation spectacularly break down. Astronomers have dubbed these regions the chrono-distortion nebulae, and for a very unsettling reason. When observed, they appear to show multiple distinct events occurring in the exact same location, but each event is separated by years, decades, or even centuries. It is as if we are looking at a cosmic photograph with multiple, overlapping exposures from different eras. These temporal ghosts present an observational nightmare. Imagine training a telescope on one of these glowing clouds and witnessing the violent death of a massive star in a supernova explosion. Then, just a few months later, you look again at that very same empty point in space and see the star still there, shining peacefully as if nothing had happened. The light from both the star's life and its death is arriving at our telescopes from the identical coordinate, but they are separated by an immense gap in time. This is not a simple light echo where light bounces off distant dust and arrives later. This is light from two different moments in a single object's history arriving concurrently, a paradox that defies conventional physics. The leading explanation points to a radical warping of spacetime within these nebulae. We know from Einstein's work that massive objects can bend light, an effect known as gravitational lensing. But what we see in these clouds suggests a lensing effect of an entirely different order. Theoretically, if the nebula contained an incredibly dense, yet unseen, concentration of mass, perhaps a knot of dark matter or a cluster of intermediate black holes, it could twist spacetime into such a complex knot that multiple paths for light are created. One path might be relatively direct, while another could be a long, cosmic detour around the gravitational distortion. Light that left the source star more recently would take the short route, while light that left the same star centuries ago could finally be completing its long, arcing journey, making the past and present appear to coexist in a single, bewildering view. An even more speculative theory ventures into the realm of quantum mechanics, suggesting these nebulae might be regions where quantum effects, which usually operate on a subatomic scale, are somehow magnified to a macroscopic level. The bizarre principle of quantum superposition, where a particle can exist in multiple states at once until it is observed, might be applying to entire stars within these clouds. In this view, the star is both alive and dead, and our act of observation is what forces the nebulous region to reveal one timeline or another at random. While this remains highly theoretical, the very existence of these chrono-distortion nebulae forces us to confront the possibility that our fundamental concepts of cause and effect may be far more flexible and far stranger than we ever believed in the unique environment of NGC 1300. If the wobbling black hole and time-bending nebulae stretch the fabric of reality, the next discovery in NGC 1300 threatens to unravel it entirely. Tucked away in a quiet sector of the galaxy is a star cluster officially catalogued as HCG-07, but known to researchers by a far more telling name, the Quantum Star Cluster. This is not a collection of stars behaving strangely. It is a place where the bedrock principles of classical astronomy cease to function, replaced by the bizarre, probabilistic rules of the quantum world. Normally, stellar evolution is a predictable, if spectacular, process. A star's mass dictates its life story with near total certainty. It will burn for millions or billions of years, pass through defined stages like a red giant or a white dwarf, and meet a specific fate. In HCG-07, that certainty evaporates. Stars within this cluster do not adhere to a single evolutionary path. Advanced spectroscopic analysis reveals a star that, by all standard metrics, should be a stable yellow dwarf like our Sun, but its light signature also contains the unmistakable markers of a much older, helium-burning red giant. It's as if the star is both middle-aged and in its final stages of life at the same time. another might show the intense, hot signature of a young blue star while simultaneously emitting the X-ray burst pattern of a dying neutron star. These aren't quick transitions. The stars persist in these contradictory, superimposed states for observable periods. The most chilling aspect of this phenomenon is the role of observation itself. When astronomers focus their most powerful instruments on a single star in this cluster to resolve its true state, the superposition appears to collapse. The contradictory signals vanish, and the star settles into one defined evolutionary phase. But upon ending the intense observation period, the star's light gradually returns to its previous blurred state, holding multiple possibilities at once. This is a direct, macroscopic parallel to the quantum superposition principle, where a particle like an electron exists in a cloud of probability, occupying many potential positions until a measurement forces it to choose one. Explanations for this defiance of cosmic law range from the revolutionary to the nearly incomprehensible. One hypothesis suggests the cluster is permeated by an exotic form of energy or a field that somehow entangles the stars, causing their quantum states to become linked and amplified to a visible scale. In this view, we are not looking at individual stars, but at a single, entangled quantum system the size of a star cluster. Another, even more mind-bending theory proposes that the cluster is not a natural formation at all, but a cosmic laboratory. Could this be the result of an experiment conducted by a vastly advanced civilization, a testament to their ability to manipulate the fundamental laws of physics on a stellar scale? Or perhaps it is a natural window, a rare region where the quantum foam that underpins space-time is so thin that the true, probabilistic nature of the universe bleeds through into our classical reality. The quantum star cluster does not simply add a new mystery to the galaxies list. It forces a profound philosophical shift, suggesting that certainty itself may be an illusion, and that probability is the true ruler of the cosmos. Yet another layer of mystery in this bizarre galaxy emerges when we study the death of its most massive stars. All across the universe, the final, cataclysmic explosion of a star, a supernovae, is one of the most energetic and informative events we can witness. It's a cosmic broadcast that sends out signals across the entire electromagnetic spectrum, and crucially, it also transmits two other fundamental messengers: a tremendous burst of neutrinos and ripples in spacetime known as gravitational waves. In NGC 1300, however, that broadcast is going silent. Astronomers have visually confirmed the brilliant, telltale flashes of multiple supernovae within the galaxy, watching them flare up and fade away exactly as expected. But when they turned their most sophisticated detectors to these events, they found nothing. No neutrinos, no gravitational waves. It's as if the star put on a spectacular light show for us but died in utter, profound silence. This absence of signal is a deafening contradiction to our understanding of stellar physics. In a standard core collapse supernova, the formation of a neutron star or a black hole is the main event. The incredible energy released in that collapse is what produces the massive neutrino burst, trillions of which pass through our detectors. The violent asymmetries and shocks during the explosion are what generate the gravitational waves. For a supernova to occur without these signatures is like having a massive earthquake that produces no sound. It suggests the entire internal mechanics of the collapse are fundamentally different from anything in our models. So what kind of stellar death doesn't shout its arrival to the universe? One compelling theory points to a phenomenon called a failed supernova or unnova. In this scenario, a very massive star might collapse directly into a black hole without the enormous shockwave that blows off its outer layers. Instead of a violent explosion, the star's outer envelope could simply fall inward, swallowed whole by the newly formed black hole. The visual flash we see from a distance might not be the star itself exploding, but rather a final, desperate burst of light from material just at the event horizon. or perhaps from a companion star being violently disrupted by the gravitational collapse happening next to it. This would create a brilliant optical flare that mimics a supernova, but without the neutrino-producing chaos of a neutron star formation or the strong gravitational wave signal of an asymmetrical explosion. Another, even more exotic possibility involves stars composed of previously unknown types of matter. What if certain stars in NGC 1300 are built not from regular atoms but from strange quarks? A strange star undergoing collapse would behave in ways we can barely predict, potentially quenching the mechanisms that produce neutrino and gravitational wave bursts, resulting in a quiet, implosive death. The silent supernova of NGC 1300 are not mere anomalies, they are critical clues. They suggest that our catalogue of stellar deaths is incomplete, and that the universe has quieter, more efficient ways of making black holes than we ever imagined. Each silent event is a challenge, pushing us to rewrite the final chapter in the life story of a star. Yet another profound mystery hidden within the light of NGC 1300 challenges one of the most well-tested theories in all of physics, Einstein's general relativity. This phenomenon is known as the gravity lens paradox. Gravitational lensing itself is a well-understood cosmic tool. It occurs when the immense gravity of a foreground object, like a galaxy cluster, bends and magnifies the light from a more distant object behind it, acting like a natural telescope. In NGC 1300, however, this cosmic magnifying glass is producing images that are optically impossible, creating a puzzle that has astrophysicists questioning if they need to rewrite the rules. The paradox is observed when astronomers study the distorted, magnified images of galaxies that lie far beyond NGC 1300. The lensed images appear in locations and with a clarity that the known mass of the galaxy simply cannot produce. It's as if an invisible hand is placing additional, incredibly dense lenses within the galaxy's structure, focusing light in ways that defy all calculations. In several specific cases, the lensed images of a single background galaxy are not only too bright and too well resolved, but they also appear in multiple, symmetric arrangements that current models of the galaxy's mass distribution cannot replicate. The light is being bent by something with far more gravity than the visible stars and gas can account for, but that something remains completely undetectable. This leaves scientists with two equally radical explanations. The first points to a bizarre and unknown distribution of dark matter within NGC 1300. Our standard model suggests dark matter forms a massive, diffuse halo around a galaxy. But to create these specific lensing effects, vast quantities of dark matter would need to be concentrated in precise, intricate structures, like invisible rings, arcs, or filaments weaving through the galaxy's disk. These dense clumps would act as secondary lenses, amplifying the light in their specific paths. Finding such organized, dense formations would completely overturn our understanding of how dark matter behaves and clusters on a galactic scale. The second, and even more profound, possibility is that Einstein's theory of general relativity, while impeccably tested within our solar system, might require modification when applied across the immense scales of an entire galaxy. Some researchers propose theories like modified Newtonian dynamics, which suggest that gravity behaves differently at extremely low accelerations, such as those found in the outer reaches of galaxies. Under MND, the gravitational force wouldn't weaken as quickly as general relativity predicts, which could potentially account for the extra lensing power without the need for unseen dark matter clumps. NGC 1300's lensing paradox provides a critical testing ground for these competing ideas. It forces a fundamental question: are we missing a major component of the universe's mass, or are we simply wrong about how gravity itself works on the largest scales? This single galaxy might hold the key to one of the biggest debates in modern cosmology. While the silent supernova and gravitational lensing paradox present deep theoretical challenges, another anomaly in NGC 1300 confronts us with a different kind of mystery, one not of strange signals but of a profound and targeted silence. Within a sweeping section of one of its grand spiral arms, astronomers have mapped a colossal region of space, hundreds of light years across, that is completely and utterly mute. This is the radio void, a volume of the galaxy that emits absolutely no radio waves whatsoever. In a universe that crackles with the static of cosmic background radiation, the steady hum of pulsars, and the faint hiss of interstellar gas, this perfect silence is not just unusual, it is deeply unnatural. Radio astronomy gives us a unique view of the cosmos, one that often reveals processes invisible to optical telescopes. Young, hot stars flood their surroundings with radio waves. Supernova remnants, the expanding shells of ancient stellar explosions, are brilliant radio beacons for millennia. Even the cold, dark molecular clouds where new stars are born emit a faint radio whisper as their molecules gently vibrate. The region within the radio void contains all of these things. Telescopes can see the brilliant visible light of stars and the glowing gas of nebulae, confirming that this area is brimming with astrophysical activity. Yet, when they tune their radio dishes to listen in, they are met with a perfect blanket silence. It is as if a cosmic volume knob has been turned all the way down, selectively muting only this specific frequency band across this entire vast expanse of space. This isn't merely an absence of strong sources, it is a complete lack of all radio emission, down to the faintest background levels that permeate every other part of the galaxy. Such a perfect void suggests an active process of suppression, not just a lack of emitters. One compelling explanation points to an exotic form of interstellar absorption. Perhaps this region is filled with an unknown type of dust or plasma cloud that doesn't just block radio waves, but perfectly absorbs them across the entire spectrum, converting their energy into some other undetectable form. This would be like a sponge designed to soak up only one color of light, leaving all others untouched. An even more fascinating possibility involves the fundamental properties of space itself within this void. The vacuum of space isn't truly empty. According to quantum field theory, it is a seething foam of virtual particles popping in and out of existence. What if the conditions within this region alter this quantum foam in a way that prevents the propagation of radio frequency photons? In this scenario, the radio waves are being generated by stars and nebulae just as they are everywhere else, but they cannot travel through this distorted spacetime. They are effectively stillborn, unable to escape the volume in which they are created. This would mean the void is not a region of silence, but a region of imprisonment for a specific type of light. The implications of either scenario are staggering. If a natural absorption material is responsible, its discovery would revolutionize our understanding of interstellar chemistry and physics. If the void is caused by a localized distortion of quantum vacuum properties, it would provide us with a rare, large-scale laboratory to test some of the most abstract theories in modern physics. The radio void of NGC 1300, in its utter silence, may be screaming clues about the most fundamental workings of the universe, challenging us to listen not for what is there, but for why something so universal is so conspicuously missing. But the mystery of NGC 1300 doesn't end with silent explosions and missing radio waves. Deep within its spiral arms, another discovery glitters with an almost impossible beauty. Scattered throughout the galaxy are vast, shimmering clouds of interstellar dust, a common enough sight. Yet when astronomers analyzed the light filtering through these clouds, they found a signature so strange it defied all known catalogs of cosmic materials. This dust isn't the familiar, amorphous grime of carbon and silicates found throughout the universe. Instead, it's composed of microscopic crystals arranged with a breathtaking, near-perfect geometric order. We're not talking about small mineral grains. These are clouds light years across that behave like single, gigantic crystalline structures, reflecting and refracting light in unified, precise ways never before seen in the void of space. The existence of such macroscopic crystalline formations shatters our understanding of how dust forms and behaves. In normal conditions, interstellar dust is chaotic. It's the soot from dying stars, the ash from supernovae, and the frozen ices that accumulate in cold molecular clouds. These particles are jagged, irregular, and disorganized. For a cloud of this dust to somehow organize itself into a coherent crystalline matrix, with trillions upon trillions of particles aligning their structures perfectly across vast distances, would require conditions so specific and so stable they are thought to be virtually impossible in the turbulent environment of a galaxy. It would be like throwing a bucket of sand into a hurricane and having it fall to the ground as a flawless, polished sheet of glass. So how did these crystal clouds come to be? One theory points to a forgotten and incredibly ancient stellar process. Perhaps a generation of stars that lived and died billions of years before the galaxy took its current form were fundamentally different from the stars we see today. These primordial stars might have had unique compositions that, when they reached the end of their lives, did not simply expel dust, but rather seeded the surrounding space with a rain of perfectly formed crystalline nuclei. These microscopic seeds would then act as templates, forcing any new dust that later drifted into the region to conform to their perfect lattice structure as it condensed, slowly building these enormous crystal clouds over eons. An even more captivating idea involves the influence of the galaxy's own magnetic fields. NGC 1300 is a barred spiral, a shape that generates immensely powerful and complex magnetic currents flowing along its arms. It's possible that these magnetic fields are so strong and so orderly in certain regions that they act like a cosmic loom, weaving the chaotic dust particles into alignment. Each tiny dust grain likely has a slight magnetic charge, and under the influence of this pervasive force, they are compelled to spin and orient themselves into a unified crystalline formation, much like iron filings arranging themselves along the field lines of a magnet. This would mean we are not looking at a frozen sculpture, but at a dynamic, living structure constantly being woven and maintained by the invisible magnetic fabric of the galaxy itself. The implications of these crystalline clouds reach far beyond mere curiosity. Their perfect structure would make them incredibly efficient at promoting the formation of complex molecules. The ordered surfaces of the crystals could act as a catalyst, providing a stable foundation for atoms to meet and bond into the prebiotic building blocks of life, sugars, amino acids, and more on a scale and at a speed unthinkable in our own messy corner of the universe. This single, beautiful anomaly suggests that NGC 1300 might not only be a gallery of cosmic wonders, but also a nursery for complexity, potentially setting the stage for life in ways we are only beginning to imagine. Peering even deeper into the intricate structure of NGC 1300, astronomers have uncovered a feature so subtle it was completely invisible until we learned to look at the galaxy in an entirely new light. Stretching out from the main body of the barred spiral is an ethereal, additional arm, a faint, ghostly appendage that doesn't appear in standard optical images. This spectral structure only reveals itself when we observe the galaxy in very specific, non-visible wavelengths, like the faint emission of ultraviolet light and the subtle whispers of certain radio frequencies. It's been dubbed the Phantom Spiral Arm, and its existence is more than just a neat curiosity. It's a direct challenge to our most fundamental models of how spiral galaxies are built and maintained. A spiral galaxy's iconic shape isn't fixed like a sculpture. It's a dynamic pattern, a density wave that moves through the galaxy's disk. As this wave passes through, it compresses gas and dust, triggering the birth of brilliant new stars that illuminate the arm's leading edge. This is why we see spiral arms so clearly. They are lined with short-lived, luminous blue stars. The phantom arm defies this entire process. It has the distinct curved structure of a spiral arm, but it is almost completely devoid of these young, bright stars. It's a pattern without the usual source of its own illumination, a cosmic shape etched into the galaxy with invisible ink. This means the density wave theory alone cannot explain its presence. There must be another unseen force at work, sculpting and sustaining this structure. This is where the invisible hand of dark matter enters the picture. We believe every galaxy is embedded within a vast, diffuse halo of this mysterious substance. The prevailing theory suggested this halo was roughly spherical, providing the gravitational glue that holds the galaxy together but not directly influencing its internal, visible structure. The phantom arm forces a radical rethink. To maintain a coherent spiral structure without the constant star formation that normally defines it, there must be an immense, persistent gravitational influence. The most compelling explanation is that the dark matter halo of NGC 1300 is not a smooth, featureless sphere. Instead, it may have its own complex topography, dense clumps and asymmetrical ripples within the halo itself. Imagine the dark matter halo not as a featureless cloud, but as a landscape of invisible hills and valleys. The phantom spiral arm could be a place where a particularly dense ridge of dark matter lies beneath the galactic disk. This concentration of mass would exert a powerful gravitational pull, enough to permanently warp the disk of the galaxy and trap stars, gas, and dust into its enduring pattern. In this scenario, the arm isn't a temporary wave of star formation. It's a permanent fixture, a gravitational well so deep that it dictates the structure of the visible galaxy from the shadows. We are not seeing a wave passing through the galaxy. We are seeing the galaxy conforming to the hidden architecture of its own dark matter skeleton. The implications of this are profound. If true, it means that the beautiful spiral patterns we see in galaxies across the universe may not be transient phenomena at all. They could be the permanent imprint of the dark matter distribution, a cosmic fingerprint left on the visible matter. This would completely change how we model galaxy evolution and growth. The phantom arm is more than a ghost. It's a messenger, offering us a rare glimpse into the invisible framework that dictates the shape of everything we see. It suggests that to truly understand a galaxy, we must learn to see not just the glittering stars, but the dark, sculpting hands that mold them. While the phantom arm reveals the hidden influence of dark matter on galactic structure, our next destination within NGC 1300 presents a mystery that defies the very timeline of a star's existence. In a region catalogued as Sector Theta 9, astronomers have found stars that appear to have been granted a cosmic second act. This is the stellar resurrection zone, a place where the unbreakable rule of stellar evolution, that stars only grow older and never younger, seems to have been spectacularly broken. Here, telescopes have captured the unmistakable, blazing light of massive blue stars, objects that typically burn bright and die young in a few tens of millions of years. Yet, surrounding these youthful giants are the ancient, cooling remnants of planetary nebulae, the glowing, discarded outer layers of stars that have already ended their lives. The spectral signature is a baffling contradiction. These stars show the intense hydrogen fusion and powerful stellar winds of an object in its boisterous prime. But their light is also polluted with the heavy element ash that is only forged in the furious furnaces of a supernova or the final throes of an aging giant. It is as if a grandparent and their grandchild were somehow the same person, simultaneously displaying the vitality of youth and the wisdom of extreme age. This resurrection is not a one-off event. Multiple stars in this sector display this impossible combination of traits, pointing to a localized phenomenon rather than a series of observational errors. The immediate and most dramatic explanation invokes a process of exotic matter accretion. What if these stars are not being reborn, but are instead undergoing a radical transformation? One theory suggests they are white dwarfs, the Earth-sized, incredibly dense cores of dead stars that have pulled a neighboring star into a deadly embrace. As the white dwarf gravitationally steals matter from its companion, this stolen fuel accumulates on its surface. Once a critical mass is reached, it can trigger a runaway thermonuclear explosion across the entire star's surface. This event, known as a nova, does not destroy the white dwarf but does make it shine with tremendous brilliance, momentarily mimicking a much younger, massive star. However, even a series of nova eruptions cannot fully account for the sustained, youthful energy output and the specific elemental pollution observed in these resurrected stars. This has led to an even more exotic proposal, the accretion of strange matter. Hypothetical strange stars, theorized to be made of up, down, and strange quarks, could possess properties that allow them to appear vastly different depending on their environment. A dormant strange star, cool and dark, could be reignited into a blazing sun-like state if it begins accreting a sufficient amount of normal matter, triggering a transformation in its very quantum structure. This would be a true resurrection, a fundamental change of state that effectively rolls back the cosmic clock. Beyond these dramatic ideas lies a possibility that rewrites our textbooks entirely: the existence of a previously unknown stellar evolutionary pathway. Our current models are based on a universe filled with normal matter. But what if the conditions within Sector Theta 9 are unique? A pervasive, exotic form of energy or a local fluctuation in the fundamental constants of physics could allow for stars that cycle through their lives differently. Perhaps certain stellar remnants can, under the right conditions, reinitiate stable fusion in their cores through a process we have not yet conceived, moving backward along the evolutionary track in a way that nature prohibits everywhere else in the universe. The stars of the resurrection zone stand as monumental challenges, not just to what we see, but to what we believe is possible. They suggest that the life cycle of a star may not always be a one-way street toward death and darkness, but that under the right, mysterious circumstances, a glorious and impossible rebirth might just be within reach. Venturing further into the uncharted territories of NGC 1300, we encounter a nebula that doesn't just challenge our understanding of physics, it seems to rewrite the rulebook for reality itself. Designated G0.55, but more famously known as the Quantum Entanglement Nebula, this vast cloud of gas and dust is the site of a phenomenon so bizarre it was once thought to be completely impossible. Within its glowing confines, the spooky, invisible threads that bind the quantum world are not just present, they are stretched to a scale that defies everything we know. Quantum entanglement is the strange process where two particles become linked, their fates intertwined no matter how far apart they are separated. A change to one particle will instantly affect its partner, a connection that seems to operate faster than the speed of light. This isn't just theory, we've proven it in laboratories on Earth, but there's a catch, a fundamental limit we believed was unbreakable. In every experiment ever conducted, this delicate quantum connection is incredibly fragile. The slightest interaction with the outside environment, a passing photon, a stray atom, will destroy the entanglement in a process called decoherence. Because of this, the farthest distance we've been able to maintain entanglement between particles on Earth is a few hundred miles at most. The near infinite number of particles and forces in the chaotic environment of a nebula should make entanglement over any significant distance an absolute impossibility. And yet, the Quantum Entanglement Nebula does the impossible. Astronomers detected this by using the nebula itself as a natural laboratory. They focused on pairs of particles born from the same energetic event within the cloud, like a photon splitting into an electron and a positron. According to all known laws, these twin particles should have lost their quantum connection almost instantly as they flew light years apart through the dense nebula. But when researchers measured the properties of one particle, they found its distant twin, now separated by an entire light year of space, responded instantaneously. Its spin, polarity, or momentum always correlated perfectly with its partner's measurement, a coordination that could only be explained by a sustained, unbroken quantum link. They were still entangled, their fates locked together across a void that should have severed their connection trillions of times over. This observation sends shockwaves through the foundations of quantum mechanics. How can this connection possibly survive in such a hostile environment? One radical theory suggests the nebula is not a normal cloud of gas, but a region where the fundamental nature of spacetime is different. Perhaps the vacuum energy here is so low that decoherence is dramatically suppressed, creating a kind of cosmic quiet room where quantum states can persist far longer than anywhere else. This would be a place where the background hum of the universe is turned down to a whisper, allowing these fragile connections to remain intact. An even more profound possibility involves the role of dark energy, the mysterious force accelerating the expansion of the universe. Some cutting-edge models propose that entanglement might not be a phenomenon confined to particles, but is actually woven into the fabric of spacetime itself, with dark energy acting as the medium that transmits the connection. In this view, the quantum entanglement nebula could be a place where the local concentration or behavior of dark energy is uniquely aligned to support and strengthen these quantum links across vast distances, effectively providing a cosmic network that reinforces the entanglement against environmental disruption. The implications of this are staggering, reaching far beyond a single strange nebula. If quantum entanglement can be maintained over light years, it opens up the possibility of a universe deeply interconnected in ways we never dreamed. Information could be transferred or correlated across vast distances instantaneously, challenging Einstein's strict cosmic speed limit. Furthermore, it provides a potential mechanism for one of the biggest mysteries in cosmology: how the universe achieved such a uniform temperature and structure in its early moments, a problem known as the horizon problem. If distant parts of the early cosmos were quantumly entangled, they didn't need to exchange signals at the speed of light to be coordinated. They were born connected. The quantum entanglement nebula might not just be a cosmic oddity. It could be a preserved relic from the birth of the universe, showing us that the spooky connections of the quantum world are, in fact, the fundamental threads that bind the cosmos together. Moving from the entangled connections of the quantum realm, we now explore a phenomenon that warps the very fabric of time itself. Deep within the spiral arms of NGC 1300, astronomers have identified a series of interstellar clouds that defy our uniform experience of time. These are the time dilation gas clouds, vast nebulous regions where clocks would not tick in sync with the rest of the universe. The discovery was made not by observing clocks, but by watching the fundamental pace of chemistry. Within these clouds, complex molecules form, break apart, and recombine at wildly different rates. In one cloud, the formation of a simple water molecule might unfold in what we would perceive as slow motion, while in a neighboring cloud just a few light years away, the furious cascade of reactions building complex organic compounds appears to be on fast forward. This variance isn't a simple observational trick or an effect of the clouds moving at relativistic speeds. The differences are localized and extreme, suggesting the flow of time itself is being altered by the properties of the cloud. The primary method for measuring this relies on molecular clocks. Certain chemical reactions, like the formation of formaldehyde or the isomerization of hydrogen cyanide, have very well understood and predictable rates under specific conditions of density and temperature. By mapping these reactions across different parts of the same cloud, scientists found these reliable cosmic clocks were running at significantly different speeds. In some regions, reactions predicted to take centuries were completing in mere decades, while in others, processes that should be rapid were stretched out over millennia. What could possibly cause time to become so malleable within these pockets of gas and dust? The leading explanation draws from Einstein's theory of general relativity, which tells us that gravity warps spacetime. If these clouds contain concentrations of mass far greater than their visible material suggests, their gravitational pull could be creating a significant time dilation effect. This points directly to the hidden hand of dark matter. Imagine if these clouds are not just balls of gas, but are instead trapped within immense, invisible knots of dark matter. The combined gravitational influence of the normal gas and this unseen mass would be enough to slow time perceptibly within the cloud's volume relative to the outside universe. The greater the density of the dark matter knot, the more pronounced the time warp would be. However, an even more intriguing possibility moves beyond gravity entirely. Another theory suggests the answer may lie in the vacuum of space itself. Quantum physics tells us that a vacuum is not truly empty, but is seething with virtual particles that constantly pop in and out of existence. The average energy of this quantum vacuum is known as the zero-point energy. What if the value of this zero-point energy is not constant throughout the galaxy? If these clouds exist in regions where this fundamental energy field is lower or higher than the galactic average, it could directly influence the rate at which quantum processes and, by extension, all chemical reactions occur. A higher zero-point energy might provide a background push that accelerates interactions between particles, effectively speeding up time for chemistry within that cloud. Conversely, a lower energy would slow everything down. This would mean we are not seeing the effect of gravity on time, but rather the effect of the very ground state of the universe on the passage of events. The existence of these clouds does more than just add another mystery to the list. It provides a unique cosmic laboratory. By studying the specific reactions that are sped up or slowed down, we could potentially map the distribution of dark matter in a completely new way using chemistry as our guide. Or we might be able to measure variations in the quantum vacuum itself, something that has never been done before. These clouds challenge the notion that time is a universal constant, suggesting instead that it is a fluid, local property, deeply connected to both the hidden mass of the universe and the invisible energy that fills its emptiness. But the strange manipulations of time within NGC 1300 are not the only way this galaxy defies the expected balance of the cosmos. If we turn our attention to a seemingly unremarkable patch of its galactic disk, we find a spectacle of pure, raw contradiction, a brilliant fountain of light not from new stars but from the violent death of matter itself. This is the antimatter fountain, a sustained jet of positrons, the antimatter counterparts to electrons streaming out from a point in space where absolutely nothing should be able to produce them. Antimatter is the ultimate cosmic fugitive. For every particle of normal matter, there is an antimatter twin with opposite charge. When matter and antimatter meet, they annihilate each other in a flash of pure energy, a process that is 100% efficient. Because of this, antimatter is incredibly rare in our universe. It was mostly all annihilated in the first moments after the Big Bang, leaving behind the normal matter that makes up everything we see. Today, we only find tiny, fleeting amounts of it, created in high-energy events like lightning storms on Earth or around pulsars and black holes. But these sources only produce minuscule quantities that are instantly destroyed. The fountain in NGC 1300 is different. It is not a brief spark, it is a continuous, focused geyser, pumping out a vast and steady stream of positrons that flows for light years before finally dissipating. It's as if a hidden cosmic fire hose is spraying the essence of antimatter into a galaxy made of its mortal enemy. The very existence of this fountain presents two staggering mysteries. First, how is such an enormous volume of antimatter being created? The known mechanisms are simply not powerful enough. Even the most energetic events we know of, like a hypernova or a colliding neutron star binary, would produce a one-time burst, not a stable, long-lasting fountain. This suggests a source that is both unimaginably energetic and perfectly steady, operating on a timescale that dwarfs human comprehension. Second, and perhaps even more baffling, is how this antimatter is being contained. For the positrons to form a coherent jet, they must be streaming away from their source without immediately encountering normal matter and annihilating. This implies the existence of some kind of magnetic or gravitational nozzle, a focusing mechanism that keeps the antimatter isolated and channeled as it travels, preventing it from touching the sides of its own lethal pipeline. The hunt for an explanation leads us to the very edge of known physics. One compelling theory involves a specific type of hyper-advanced pulsar, a magnetar with a magnetic field so strong it warps the very vacuum of space around it. In such an extreme environment, it's theorized that the magnetic field could be so powerful it literally rips particle-antiparticle pairs from empty space itself, a process known as spontaneous pair production. This magnetar could then be acting like a cosmic particle accelerator, ejecting the antimatter component in a tightly collimated beam while somehow containing the normal matter. An even more exotic proposal points to the decay of a hypothetical particle that has never been directly observed, the photino. In certain theories of supersymmetry, which propose a heavier partner particle for every known particle in the standard model, the photino is the partner of the photon. If these particles were created in the early universe and are stable, they could have accumulated into vast, invisible clumps. The slow, steady decay of these photinos over billions of years could be producing a constant drizzle of positrons, a faint signal that would be unnoticeable almost anywhere else. But if a dense cluster of these particles were to be concentrated in one spot in NGC 1300, their combined decay could appear as a brilliant fountain of antimatter, a beacon of new physics shining from an otherwise dark and silent corner of the galaxy. This astonishing structure is more than a cosmic light show. It is a direct challenge, forcing us to consider that the universe might harbor factories of creation far stranger and more powerful than anything we have yet dared to imagine. Tucked away from the brilliant star clusters and luminous nebulae, there exists a region in NGC 1300 that is the astronomical equivalent of a silent movie, a place where the most dramatic act of cosmic creation plays out in utter darkness. This is the Dark Star Nursery. Unlike every other stellar nursery we've ever found, this one gives off no light, no glow of heated gas, no infrared warmth from dense dust clouds, no radio whispers. It is a void within a void, completely invisible to every type of telescope we have. Its discovery was not a matter of seeing something, but of noticing that something was profoundly and inexplicably missing. Astronomers were meticulously mapping the rotation of the galaxy when they noticed a peculiar gravitational tug in a specific sector. The motions of visible stars at the edge of this region were being subtly altered, as if they were orbiting an immense unseen mass. The sheer concentration of this hidden gravity was the first clue. Then came the even more peculiar detail. The gravitational pull wasn't from a single point-like source like a black hole. Instead, it had the sprawling, complex signature of a vast structure, one that was dynamically collapsing and forming clumps in a way that perfectly mirrored the early stages of star formation. They were watching the gravitational ballet of protostars condensing from a cloud, but they could see only the dancers' shadows on the wall. The stars themselves were missing. This pointed to one staggering conclusion. Stars were being born here from a material that does not interact with light in any way. This isn't just dark dust, it is something fundamentally different. Normal star formation begins when a cloud of molecular hydrogen and dust collapses under its own gravity, heating up until nuclear fusion ignites and a star is born. Here, that entire process is happening with a substance that remains completely dark and cold throughout. These nascent stars, these dark protostars, possess immense gravity, but they emit no radiation whatsoever. They are massive gravitational ghosts, so what could this dark material be? The most thrilling possibility is that we are witnessing the direct collapse of dark matter itself. Our standard model posits that dark matter particles only interact with each other and normal matter through gravity, making it impossible for them to clump together tightly enough to form stars. They just form diffuse halos. But what if our model is incomplete? What if, under certain extreme conditions, dark matter particles can interact with each other through a new, unknown force? This could allow them to shed energy, collapse, and form dense structures like dark stars. These objects wouldn't shine from fusion. They would be powered by the annihilation of dark matter particles within their cores, a process that would release enormous energy but could theoretically do so in a way that emits no light, only gravitational waves. An alternative, equally astounding theory suggests this nursery is forming stars from a hypothetical form of matter. One candidate is the cue ball, a theoretical supersymmetric particle that could coalesce into large macroscopic clumps. Another is mirror matter, a parallel form of matter that has its own set of particles and forces, but only interacts with our matter through gravity. A cloud of mirror matter could undergo its own version of star formation right beside our own, completely invisible to us except for the gravitational footprint it leaves behind. The implications of the dark star nursery are monumental. If confirmed, it would be the first direct evidence that dark matter or other exotic substances can form complex structures, opening up an entire new branch of astrophysics. It suggests that a galaxy's true anatomy includes not just the glittering stars we see, but a parallel, shadowy skeleton of dark stars, hidden from view but shaping everything through their gravity. This nursery forces us to accept that the universe might be filled with an entire unseen ecology of celestial objects, living and dying in the darkness right beside the luminous universe we know. While the dark star nursery hints at structures built from invisible matter, another discovery in NGC 1300 points to a flaw in the very fabric of spacetime itself. Among the most perplexing signals ever detected from this galaxy are a series of gravitational wave patterns that stand out from all others. Unlike the familiar chirps and rumbles created by colliding black holes or neutron stars, these signals are persistent monochromatic hums, unwavering in their frequency and astonishing in their power. After years of analysis, researchers arrived at a stunning conclusion. These patterns are a near-perfect match for the theoretical predictions of cosmic strings. A cosmic string is not an object in the way we normally think of one. Imagine the universe in its earliest, hottest moments after the Big Bang, a seething cauldron of energy undergoing a series of rapid phase transitions, much like steam cooling and condensing into water. Theorists propose that during one of these transitions, the fabric of spacetime itself might not have cooled evenly. Tiny, microscopic defects could have been frozen into existence as the cosmos expanded. These defects would be unimaginably thin, far smaller than a single atom, but they would stretch across incredible distances, potentially across the entire length of a galaxy. They are not made of matter, they are pure energy, flaws in the geometry of the universe, and they would possess immense density, with a single inch of a cosmic string potentially weighing as much as a mountain. The gravitational wave signature of such an object is what makes it detectable. A cosmic string under tension would vibrate or oscillate, sending out ripples in spacetime at specific, pure frequencies. If a string were to loop and collapse, or if two strings were to cross and reconnect, the event would unleash a tremendous burst of gravitational radiation. The signals from NGC 1300 show exactly this kind of activity, a steady background hum consistent with a vibrating string, punctuated by sharp, energetic bursts that look like cosmic snapping or splicing events. It's the sound of spacetime itself ringing like a plucked violin string. The confirmation of a cosmic string would be one of the most significant discoveries in the history of cosmology. For starters, it would provide direct, tangible evidence for the physics of the very early universe, offering us a glimpse into the high-energy processes that occurred just fractions of a second after the Big Bang. we could finally test the grand unified theories that attempt to describe how the fundamental forces of nature were once merged into a single superforce. The specific properties of the string, its thickness, the frequency of its oscillations, would act as a fingerprint telling us exactly which phase transition created it and at what energy scale it occurred. Furthermore, the immense gravitational pull of a cosmic string would have acted as a seed for the formation of the largest structures we see in the universe. The great cosmic web of galaxies and galaxy clusters, stretching across billions of light years, might have originally condensed around a scaffolding of these primordial flaws. Finding one in NGC 1300 wouldn't just be about finding a strange object. It would be like finding the original blueprint for the cosmos, the hidden template upon which all visible matter was later draped. This faint hum from a distant galaxy is more than a curious signal. It is a potential message from the very birth of reality, a relic from a time before time, waiting for us to finally listen. Leaving behind the silent hum of cosmic strings, we now turn our attention to a discovery that strikes at the very heart of how we measure the universe. For over a century, the redshift of light has been our most trusted tool for mapping the cosmos. When light from a distant galaxy is stretched towards the red end of the spectrum, we interpret this as a Doppler effect, telling us the galaxy is moving away from us, and the degree of that shift allows us to calculate its velocity and distance. This principle is the cornerstone of modern cosmology, the key evidence for an expanding universe. But in the space behind NGC 1300, this cornerstone is cracking. Astronomers here have found a collection of background galaxies and stars that present a bewildering contradiction, now known as the chromatic redshift anomaly. The problem is this: when researchers analyze the light from these distant objects, they don't get a single, consistent redshift value. Instead, the redshift measured depends entirely on which color of light you're looking at. For a single galaxy, its blue light might suggest it's moving away at one speed, while its red light tells a completely different story, and its infrared light tells a third. It's as if the different colors of light from the same source have taken wildly different journeys to reach us, arriving with conflicting reports on how much the universe has stretched during their travel time. This isn't a small margin of error. The discrepancies are large, systematic, and they completely violate the standard cosmological principle that the redshift of an object is a uniform property of its motion. This anomaly forces us to confront a difficult question. What if the redshift of light isn't always a reliable indicator of velocity and distance? The implications are staggering, potentially throwing a century of cosmological measurements into doubt. If this effect is real and widespread, it could mean that our maps of the universe, our estimates of its age, and even our understanding of dark energy's accelerating expansion are built on a foundation that is shakier than we ever imagined. The entire cosmic distance ladder, the step-by-step method we use to measure the vast scales of the universe, could have a fundamental flaw running through its most important rung. So what could be causing light to betray its own message in this way? One family of explanations looks for something in the space between us and those background galaxies that is interacting with light in a new, unknown way. Perhaps the vast interstellar medium of NGC 1300 is not uniform. It might be filled with a previously undetected type of particle or plasma that scatters shorter wavelengths of light, like blue, differently than longer wavelengths, like red. This filtering effect could subtly alter the light's properties during its long journey, making it appear as though some colors have been more redshifted than others. It would be an immense cosmic illusion, a trick of the light on a galactic scale. An even more radical possibility involves the properties of space itself. We know that empty space isn't truly empty, it's filled with quantum fields. What if these fields are not uniform across the universe? The region of space we are looking through toward NGC 1300 could have a different texture or energy density. This varying vacuum could potentially affect different wavelengths of light in different ways, imparting a false redshift signal that has nothing to do with the motion of the source galaxy. In this view, the redshift isn't measuring velocity, it's measuring a local property of the spacetime that the light traveled through. This chromatic anomaly does more than just present a puzzle. It serves as a crucial reminder that our instruments for understanding the cosmos, no matter how refined, are still interpreting signals based on a set of rules we assume are constant. The light from these distant galaxies is a messenger, but its message is being garbled by a process we do not yet understand. Unraveling this mystery is not just about fixing a chart. It is about learning a new language of the universe, one where light itself may have more to tell us than simply how fast something is moving away. Amidst the grand tapestry of forces that govern our universe, magnetism has always been a fundamental duality. Every magnet we've ever found, from a simple refrigerator decoration to the powerful fields of a neutron star, comes with an inseparable pair of north and south poles. This is not just an observation, it is a cornerstone of our physical laws, deeply embedded in James Clerk Maxwell's equations that describe electromagnetism. Cut a magnet in half and you don't get isolated poles, you simply get two new, smaller magnets, each with its own north and south. The existence of a particle with only one magnetic pole, a magnetic monopole, has been a theoretical ghost, a tantalizing possibility predicted by some grand unified theories but never observed. Until we looked at NGC 1300, scattered throughout this galaxy are turbulent regions of space that astronomers have termed magnetic tempests. These are not ordinary storms of charged particles. They are vortices where the magnetic field lines do something inexplicable. Instead of flowing in continuous loops from one pole to another, as they do everywhere else in the universe, the field lines within these tempests appear to begin or end at a single specific point. It is as if there is a tiny, singular source or sink for magnetism, a fountainhead from which magnetic field lines emanate in all directions, or a drain into which they all disappear. The signature of this event is a highly specific and intense distortion in the polarization of light passing through these regions, a clear fingerprint that points to one staggering conclusion: the presence of magnetic monopoles. The detection of even a single magnetic monopole would be a revolution in physics, and the data from NGC 1300 suggests we are looking at entire storms of them. This isn't just about finding a new particle, it's about rewriting the textbooks. Maxwell's equations, which have stood unchallenged for over a century, are beautifully symmetric for electric charges. Positive and negative charges exist independently. But for magnetism, that symmetry has been broken. The equations show a perfect symmetry between electricity and magnetism, but nature has never provided the magnetic counterpart to an electric charge. The existence of magnetic monopoles would restore that deep and elegant symmetry, completing the equations in a way that physicists have dreamed of for generations. It would mean that magnetism is not a fundamentally different force, but one that operates under the same fundamental rules as electricity. The implications cascade far beyond tidying up some old math. The grand unified theories, which attempt to describe how the electromagnetic, weak, and strong nuclear forces were once a single, unified force in the early universe, almost universally predict the creation of magnetic monopoles in the unimaginably hot first moments after the Big Bang. Finding them would be the first direct experimental evidence that these theories are on the right track, providing a crucial window into the universe when it was only a fraction of a second old. Furthermore, the properties of these monopoles, their mass, their charge, would act as a precise diagnostic tool, telling us exactly at what energy scale this grand unification occurred and potentially pointing the way toward an even more profound theory of everything. The storms in NGC 1300 present another layer of mystery, their sheer abundance. Cosmological theories suggest that if monopoles were created in the early universe, their incredible mass would have made them incredibly rare, and they should be spread thinly across the vast expanses of space. The fact that we see evidence for what appears to be clusters or swarms of them in specific locations suggests a mechanism that is actively concentrating them, or perhaps even creating them anew. One extraordinary possibility is that the galaxy's core, with its unique and violent history, might be acting as a factory. The immense energies involved in the wobbling supermassive black hole or the cataclysmic events that might have ejected its predecessor could provide the conditions necessary to forge these primordial particles, a process we thought had ended 14 billion years ago. Another, more serene theory suggests that monopoles are not being created but collected. The galaxy's powerful magnetic fields, which weave through its spiral arms, could be acting like cosmic fishing nets, trawling the interstellar medium over billions of years and gathering these rare particles into dense clusters. The tempests we observe would then be the visible signature of these concentrated knots of monopolar charge, their combined magnetic influence finally becoming strong enough for our instruments to detect. Whether they are being born or being gathered, the magnetic monopole storms of NGC 1300 are not a relic of the past. They are a dynamic and ongoing phenomenon, a constant challenge to our understanding of the forces that shape reality itself. Yet another profound layer of this galaxy's mystery invites us to consider the nature of nothingness itself. We often think of the void between stars as truly empty, a perfect vacuum. But quantum physics tells us that even the deepest, darkest reaches of space are not truly empty. They are a seething, bubbling foam of virtual particles that spontaneously pop into and out of existence, a background energy field known as the quantum vacuum. Across the observable universe, the energy density of this vacuum is believed to be constant, a value we call the cosmological constant, which is thought to be the driver behind the accelerating expansion of the universe. But in specific regions of NGC 1300, this fundamental assumption appears to break down. Here, the energy of seemingly empty space is not constant at all. It fluctuates wildly, creating pockets where the very nature of nothingness is fundamentally different. The observable effects of these quantum vacuum fluctuations are not subtle. In one sector, astronomers have measured a localized acceleration of the universe's expansion that is significantly faster than the surrounding galactic space. It's as if a powerful, invisible engine is embedded within the void, pushing spacetime apart with unexpected vigor. In a neighboring region, the opposite occurs. The expansion appears to slow, as if the vacuum energy has dropped, creating a gravitational drag against the cosmos's outward rush. These aren't mere mathematical curiosities, they have tangible consequences. The strange lensing effects we see in the gravity lens paradox, for instance, could be partly explained if the light from distant galaxies is passing through these patches of altered vacuum energy, where the changed properties of spacetime itself are bending the light in unexpected ways. What could cause the vacuum of space to have such dramatically different energy levels in one galaxy? One compelling explanation suggests that we are seeing the direct influence of the galaxy's structure on the quantum foam. The immense mass and complex magnetic fields of NGC 1300 could be interacting with the quantum vacuum in a completely new way. Think of spacetime as a fabric. In most places, it's relatively smooth, but the combined gravitational pull of the galaxy's visible matter, its dark matter halo with its complex topography, and the powerful currents of its magnetic fields could be stretching and warping this fabric so severely that it alters the behavior of the quantum fields that live within it. This warping could suppress or excite the production of virtual particles, effectively turning the energy of the vacuum up or down like a cosmic dimmer switch. An even more profound possibility is that we are witnessing the breakdown of the cosmological constant as a universal rule. The idea that dark energy is perfectly uniform everywhere is a simplifying assumption in our models, but it may not reflect reality. Perhaps dark energy is not a constant force but a dynamic field that can clump and vary in density, much like dark matter seems to do. In this view, the fluctuations in NGC 1300 aren't an anomaly. They are a glimpse of the true, varied nature of dark energy. The galaxy might be acting as a colossal attractor for this energy, or it might contain regions where this dynamic field is interacting with itself, creating peaks and troughs in its strength. This would mean that the acceleration of the universe isn't a uniform tide lifting all galaxies equally, but a complex, shifting landscape of currents and eddies that could dictate the large-scale structure of the cosmos in ways we are only beginning to imagine. Yet another boundary is drawn within the strange tapestry of NGC 1300, but this one does not demarcate the edge of a physical object. Instead, it defines a fundamental limit of knowledge itself. Astronomers have mapped a spherical region of space roughly 10 light-years in diameter, which they call the information horizon. Within this volume, everything appears normal. Stars shine, gas clouds swirl, and energetic processes unfold just as they do everywhere else, but no information from inside this sphere can ever reach the outside. It is a perfect and impenetrable communication barrier, a cosmic censorship field that operates exactly like the event horizon of a black hole, with one terrifying difference: there is no massive object at its center. There is nothing there at all. This horizon was discovered through a combination of extreme frustration and profound luck. Researchers were tracking a particularly bright variable star within this region, watching its predictable cycles of brightening and dimming. Then, without warning, the star simply vanished from all sensors. It didn't explode, it didn't fade. It was there one moment, broadcasting its light and radio waves perfectly clearly, and then it was gone as if a switch had been flipped. The event was not a one-time occurrence. Every object, stars, nebulae, even the faint background glow of interstellar gas that passes through this invisible boundary ceases to transmit any data whatsoever to the external universe. The light and radiation they emit appears to travel outward for a fraction of a second before hitting this spherical wall and being completely extinguished, or perhaps reflected back inward. The effect creates a perfect sphere of nothingness, a hole in the data stream of the cosmos. The implications of such a feature strike at the core of physics and philosophy. An event horizon is supposed to be a product of extreme gravity, the point of no return around a singularity where the escape velocity exceeds the speed of light. But here, gravity is normal. The pull of matter inside the sphere is no different from anywhere else in the galaxy. This means the horizon is not being created by gravity. It is being created by something else entirely, a mechanism that imposes a fundamental limit on information transfer without the need for a massive collapsed star. This suggests that the link between gravity and the limits of observation might be just one special case of a much deeper, more universal principle. One extraordinary explanation draws from the holographic principle, a radical theory that suggests all the information contained within a volume of space can actually be encoded on its two-dimensional boundary like a cosmic DVD. In this view, the three-dimensional world we experience is a projection from this information-rich surface. The information horizon in NGC 1300 could be a place where this principle breaks down or becomes visible. Perhaps this spherical boundary is a flaw in the projection, a region where the encoding of reality onto the lower dimensional surface has become corrupted or damaged. Information from within the volume can no longer be properly translated or transmitted across this damaged boundary to the outside observer. We are not looking at a physical barrier, but a limitation in the very source code of reality for that region, a bug in the cosmic software that renders everything within it unreadable. Another, even more mind-bending possibility is that this horizon is evidence of a localized change in the fundamental constants of nature. What if the fine structure constant or the speed of light itself is different inside that sphere? Even a tiny, subtle variation could have cascading effects, potentially altering how light and other information carriers interact with the fabric of spacetime. If the effective speed of causality were lower inside the horizon, it could create a barrier identical to a gravitational event horizon, where the outward push of radiation is simply insufficient to overcome the new local laws of physics. The sphere would then be a separate cosmological bubble, a universe with slightly different rules nested within our own, forever isolated from us by its own altered physics. The existence of the information horizon forces a humbling realization. The universe may be filled with absolute limits to what we can ever know, boundaries built not from matter, but from the immutable laws of information itself. Deep within the spiral arms of NGC 1300, we now encounter perhaps the most philosophically challenging of all its mysteries, a region that blurs the line between the observer and the observed, the mind and the cosmos. Designated Sector Psi 4, this area has been informally dubbed the consciousness correlation zone by the researchers who study it, and the data emerging from this pocket of space is so controversial it threatens to upend the foundational principles of scientific objectivity itself. Here, the act of measurement does not merely record reality, it appears to actively and unpredictably shape it in ways that directly correlate with the presence and intention of a conscious observer. The phenomenon was first detected not by looking at stars or gas, but by analyzing the quantum states of particles streaming from a neutron star within the sector. Scientists were running a variation of the famous double-slit experiment, a cornerstone of quantum mechanics. In this setup, particles like electrons are fired one at a time toward a barrier with two slits. Even when sent individually, these particles gradually build up an interference pattern on a detector screen behind the barrier, a pattern that suggests each particle is behaving like a wave and passing through both slits simultaneously, interfering with itself. This wave-like behavior is the default state. However, the bizarre quantum rule is that the moment you place a measuring device at the slits to determine which path the particle actually takes, the wave function collapses. The particle suddenly behaves like a single, localized object. The interference pattern vanishes, and it leaves a simple clump pattern on the screen. This observer effect is well documented in labs on Earth, but it is believed to be triggered by any irreversible interaction with a measuring device, not necessarily by human consciousness. In Sector Psi 4, this established rule breaks down. Researchers found that the collapse of the wave function, the shift from wave-like behavior to particle-like behavior, was not consistently triggered by their physical measuring equipment. Incredibly, the outcome seemed to be influenced by the conscious intention of the human researchers monitoring the experiment from light years away. In a series of blind trials, when the observers were instructed to merely watch the data stream without actively trying to determine the particle's path, the interference pattern often remained intact, even though the sophisticated measuring apparatus was technically active and recording. Conversely, when the observers focused their attention with the specific intention of pinpointing the particle's location, the wave function collapsed immediately and the particle pattern emerged. The sophisticated equipment itself was not the variable. The conscious focus of the scientists appeared to be. This correlation sent shockwaves through the scientific community, igniting a fierce debate that cuts to the very heart of what we call reality. The traditional, orthodox interpretation dismisses the findings as an elaborate coincidence or an unknown experimental error. They argue that there must be some hidden physical variable within the sector that we do not yet understand, perhaps a unique spacetime geometry or a fluctuating energy field that is mimicking the appearance of consciousness-influenced collapse. From this viewpoint, elevating consciousness to a causal role in physics is a dangerous slide into mysticism, a betrayal of the materialistic principles that have guided science for centuries. The other side of the debate, though smaller, proposes a radical paradigm shift. They point to interpretations of quantum mechanics that have existed on the fringes for decades, such as the von Neumann-Wigner interpretation, which posits that the conscious mind is indeed the ultimate cause of wave function collapse. In this view, the sophisticated instruments are just extensions. They are not themselves conscious and thus cannot cause a collapse. The final link in the chain, the act of observation by a conscious entity, is what actually pins down a single reality from the cloud of quantum possibilities. If this is true, then consciousness is not a passive byproduct of the universe. It is an active participant in its creation, a fundamental force woven into the fabric of physical law. The consciousness correlation zone, then, would not be an anomaly, but a window into this deeper, more participatory cosmos, a place where the barrier between the inner world of the mind and the outer world of the galaxy is thinner than we ever dared believe. And if the nature of reality and observation weren't perplexing enough, our next discovery in NGC 1300 suggests that the very stage upon which the cosmos plays out may be far more complex than the three dimensions we experience. In several distinct regions, astronomers and physicists have identified a set of anomalies collectively termed the dimensional bleed-through. Here, the mathematical fabric of the universe appears to be fraying at the edges, offering fleeting glimpses into the possibility of spatial dimensions beyond our own. This isn't about time travel or science fiction portals. It's about the fundamental geometry of reality manifesting in ways that challenge our most basic perceptions of space. The most compelling evidence comes from a peculiar form of gravitational lensing. As we've discussed, gravity bends light, but in these specific zones, the bending is too precise, too intricate. When light from a distant quasar passes through one of these regions on its way to our telescopes, it isn't just smeared or magnified into a simple arc. Instead, it is fractured into a complex kaleidoscopic pattern of multiple, sharply defined images arranged in geometric shapes that defy the lensing models of a purely three-dimensional universe. The patterns resemble the shadows a four-dimensional object would cast onto our three-dimensional world, a concept mathematicians call a stereographic projection. It's as if the lensing is not being caused by a single massive object, but by the gravitational influence of a higher dimensional structure that is intersecting our dimensional plane, warping spacetime in ways that are impossible for any three-dimensional object to achieve. Further support comes from the behavior of certain high-energy particles within these zones. Cosmic rays, which are atomic nuclei traveling at nearly the speed of light, have been detected with energy signatures that are simply too high. According to our current models, there's a fundamental upper limit to how energetic a cosmic ray can be, called the GZK cutoff. Particles with energies beyond this limit should have interacted with the cosmic microwave background radiation during their long journey and lost energy long before they reached us. Yet, in these specific regions of NGC 1300, detectors have recorded multiple events that blast right through this theoretical ceiling. One compelling explanation for this is that these ultra-high-energy particles aren't traveling the long way across our three-dimensional universe. Instead, they might be taking a shortcut through a microscopic, curled-up higher dimension, a concept predicted by string theory. Their immense energy isn't a mystery of production, but a clue about their path. They arrived with less energy loss because, in a way, they didn't travel as far through our familiar spatial dimensions. The theoretical framework that best accommodates these bizarre observations is the brain-world scenario, a model derived from string theory. In this view, our entire three-dimensional universe could be a membrane, or brain, floating within a higher dimensional space called the bulk. Most of the time, the forces and matter of our universe are glued to our brain, but gravity, being a function of spacetime itself, could be felt across all dimensions. The peculiar lensing effects could be the result of a massive object on a nearby brain, its gravity reaching into our dimension and warping it. The high-energy particles could be leaking from one brain to another or from the bulk itself. These regions of NGC 1300, then, might be like thin spots in the dimensional membrane, places where the barrier between our brain and the higher dimensional bulk is weak enough for these profound effects to briefly shimmer into view. This isn't just abstract mathematics, it has tangible, testable consequences. If higher dimensions are indeed spilling into our reality in these zones, we would expect to see a deviation from the inverse square law of gravity at very small distances. In simple terms, gravity should get stronger much faster as you approach a point mass if extra dimensions are involved. Incredibly, precise measurements of the orbital mechanics of tightly bound binary star systems within these specific regions show exactly this kind of deviation. The gravitational pull between them is slightly stronger than our three-dimensional models predict, as if the force lines are spreading into an unseen dimension before snapping back to our own. Each of these lines of evidence the impossible lensing, the ultra-energetic particles, and the anomalous gravity paints a consistent and staggering picture. We may not be looking at mere anomalies within our universe, but at the very seams where our universe connects to a far vaster and unimaginably more complex multidimensional cosmos. And if the strange dimensional seams and the influence of consciousness weren't enough to challenge our grasp on reality, our journey now takes us to perhaps the most profound violation of natural law within this galaxy. Regions where the universe's most unbreakable rule simply ceases to apply. Throughout the cosmos, from the explosion of a star to the melting of an ice cube, every process is governed by the second law of thermodynamics, which states that entropy, the measure of disorder in a system, must always increase. Time itself has a direction, an arrow forever flying forward from order to chaos. But scattered throughout NGC 1300 are pockets of space where this cosmic clock is not just broken, it is running in reverse. These are the entropy reversal regions, and their existence questions everything we know about time, cause, and effect. The signature of these zones is not one of explosive chaos, but of impossible, serene order. Astronomers first identified them by tracking the life cycles of vast molecular clouds, the nurseries where stars are born. In a normal cloud, gravity pulls matter together into clumps that eventually ignite as stars, a process that increases local order, but at the tremendous cost of the star burning through its fuel and radiating disorder out into the universe. The net result is always a grand increase in entropy. In these special regions, however, the opposite unfolds. Observations show massive, ancient stars at the end of their lives not exploding or collapsing, but instead seemingly unraveling. They are gently dissipating, their material spreading outward in a perfectly organized, structured manner to form pristine, cold molecular clouds. It is the equivalent of watching a shattered glass spontaneously reassemble itself on the floor, or smoke pouring back into a cigarette to form unburned tobacco. The universe here is not winding down, it is winding itself back up. This isn't merely a reversal of motion, it is a reversal of information and probability. In one documented case, a supernova remnant, the scattered, chaotic debris from a stellar explosion, was observed to slowly gather itself together over centuries. The expanding shell of hot gas reversed its course, collecting every atom and particle of dust, cooling and reorganizing itself until it formed a perfect, spinning protoplanetary disk, as if the movie of the star's death was being played backwards. The probability of such an event happening by random chance is so infinitesimally small that it effectively rounds to zero. This isn't a fluctuation, it is a sustained, localized inversion of the arrow of time itself. The implications of this are staggering, reaching far beyond a simple physics puzzle. If entropy can decrease on such a large scale, it means the fundamental distinction between past and future is not a universal constant. Cause and effect could become unmoored. In such a region, you might see a wave recede from the shore to form a perfectly shaped sandcastle, or feel heat flow from a colder object to a hotter one, defying all common experience. For any conscious being within such a zone, their perception of reality would be utterly inverted. They might remember the future and anticipate the past. Explaining how such a thing could be possible pushes the limits of theoretical physics. One compelling line of reasoning draws from the controversial concept of the anti-thermodynamic potential of dark energy. As the universe expands, dark energy accelerates that expansion, diluting matter and energy and effectively increasing the maximum possible entropy the universe can hold. Some theorists suggest that in regions where the density of dark energy is exceptionally high, this could create a kind of negative pressure on the fabric of spacetime itself, a sort of entropic gravity that pulls a system back from disorder and toward a state of higher organization. In this view, the expansion of the universe isn't just creating more room for disorder. Under specific, extreme conditions, it might actively be fighting against it. Another, even more radical theory suggests these regions are not anomalies within our universe, but are instead tiny bubbles of a universe with different fundamental laws. In the multiverse hypothesis, our universe is just one of countless others, each with its own unique set of physical constants. It is statistically possible that some of these universes could have a reversed arrow of time, where the second law of thermodynamics dictates that entropy must always decrease. The boundaries between our universe and one of these time-reversed universes could be incredibly complex and dynamic. The entropy reversal regions might be places where this boundary is thin, where the laws of a neighboring cosmos are briefly bleeding into our own, creating pockets where the natural flow of time runs in the opposite direction. These zones are not just strange curiosities, they are potential windows into the infinite variety of existence, challenging the very notion that the laws of physics we hold dear are truly universal and immutable. Nowhere are the lines between the infinitely small and the infinitely large more blurred than in the next extraordinary finding from this galaxy. For over a century, physics has been fractured, split between two incredibly successful but seemingly incompatible sets of rules. General relativity masterfully describes the force of gravity and the warping of spacetime on the grand cosmic scale, governing the motion of planets, stars, and galaxies. Quantum mechanics with equal brilliance explains the bizarre, probabilistic world of the atom and the subatomic particles that form the foundation of all matter. The holy grail of modern physics has been to find a way to unify these two theories into a single framework, a theory of everything often referred to as quantum gravity. We've had brilliant mathematical proposals like string theory and loop quantum gravity, but a crucial piece has always been missing: direct observational evidence. That evidence may now be emerging from the depths of NGC 1300 in the form of the quantum gravity signature. This signature was not found by looking for a new particle or a mysterious energy field. It was discovered by watching the very ordinary yet profoundly strange behavior of dust. In several calm, unremarkable regions of the galactic disk, far from the violent pull of black holes or the turbulence of stellar nurseries, astronomers tracked the motion of individual micrometeoroids and dust grains over many years. According to the well-tested laws of general relativity, the paths of these tiny particles should be smooth, continuous arcs, dictated solely by the gravitational curvature of spacetime from the surrounding stars. But that's not what the data showed. The trajectories of these dust grains were not smooth at all. Instead, they exhibited a faint but undeniable jitter. It was a subtle, stuttering motion, as if the particles were vanishing and reappearing infinitesimally along their path, hopping between points rather than gliding through them. This is not how objects move in the smooth, classical universe of relativity. This is exactly how particles behave in the fuzzy, probabilistic universe of quantum mechanics. The incredible implication is that we are not seeing the effect of gravity on quantum objects, but rather the quantum nature of gravity itself. In these specific regions, the gravitational field, the very fabric of spacetime, appears to be fluctuating. It's not a single, smooth curve, but a seething foam of probabilistic possibilities, a concept physicists call spacetime foam. The dust grains are so small and their mass so minute that they are sensitive to these tiniest of fluctuations in the gravitational field. Their jittery path is a macroscopic readout of the quantum gravity happening beneath the surface of reality. It's as if we've been given a microscope powerful enough to watch the pixels of spacetime itself, and we've discovered that the universe is not rendered in perfect high definition, but has a fundamental graininess, a Planck-length resolution that becomes visible under these unique conditions. What could possibly cause gravity to reveal its quantum face in these specific spots and not others? The leading hypothesis points to a resonance effect with the galaxy's overall structure. NGC 1300 is a barred spiral, and its rotating core and arms generate a complex, galaxy-wide pattern of gravitational waves, ripples in spacetime much longer and slower than those from colliding black holes. It's possible that in these specific, quiet regions, the ambient gravitational wave background from the galaxy's motion resonates with the natural frequencies of spacetime foam, amplifying the quantum fluctuations to a level where they finally become detectable. The galaxy itself is acting as a colossal tuning fork, vibrating spacetime in just the right way to make its quantum hum audible to us. An alternative and equally thrilling possibility involves the influence of the galaxy's missing central black hole. The profound nothingness at the galaxy's heart creates a unique gravitational landscape. Without the overwhelming, smoothing influence of a supermassive singularity, the subtler quantum fluctuations of gravity from all the other masses in the galaxy may not be drowned out. They can rise to the surface, their collective signal becoming strong enough in these calm eddies to gently push a dust grain off its classically predicted course. This would mean the void at the center is not an absence of phenomena, but a window into a deeper layer of physics, allowing us to see the quantum whispers that are usually shouted down by gravitational giants. This observed jitter is more than just a curious anomaly. It is a potential Rosetta Stone for theoretical physics. Each tiny hop and skip of a dust grain carries encoded information about the nature of spacetime at its most fundamental level. By meticulously analyzing the pattern of this stuttering motion, physicists could potentially distinguish between the different proposed theories of quantum gravity. Does the data better fit the tiny, vibrating strings of string theory, or the woven loops of spacetime predicted by loop quantum gravity? The quantum gravity signature offers a way to move these theories out of the realm of pure mathematics and into the domain of testable observational science. We may be witnessing the first faint signals from the final frontier of physics, a message from the base layer of reality telling us how the universe is truly built. But the quantum whispers of spacetime are not the only invisible force at work within this galaxy. As we push our observational tools to their absolute limits, we uncover another layer of the unseen, sources of power that broadcast their presence not through light, but through their ghostly influence on the material world. These are the dark radiation sources, and they represent a form of energy so alien it seems to operate outside the very framework of the universe as we know it. The discovery of this phenomenon began not with a brilliant flash in a telescope, but with a series of perplexing side effects noticed across different sectors of NGC 1300. Astronomers tracking the rotation of gas clouds found certain regions where the clouds were inexplicably heating up. There was no nearby star to provide the energy, no cluster of young, hot stars, no sign of a hidden black hole's accretion disk. The gas was simply getting warmer, as if being gently microwaved by an invisible kitchen appliance. In another instance, the chemical composition of distant nebulae was being subtly altered at an accelerated rate, with molecules dissociating and recombining as if under intense energetic bombardment. Yet, when they turned every available instrument toward the apparent source of this activity, they found absolutely nothing. No X-rays, no gamma rays, no radio waves, no infrared heat signature. The regions were dark across the entire electromagnetic spectrum. It was clear that something was pouring energy into these areas of space, but that something was completely undetectable by any conventional mean. The only conclusion was that they had stumbled upon a form of radiation that does not interact with light or matter in any way we understand, a true dark radiation. This is not dark matter. Dark matter makes its presence known solely through gravity, a persistent massive pull. This dark radiation is an active, energetic phenomenon. It transfers energy, it heats matter, it catalyzes chemical reactions, but it does so without using the electromagnetic force. It simply bypasses it entirely. This suggests we could be witnessing the effects of a previously unknown fundamental force or a novel type of interaction between particles. Our standard model of physics describes four fundamental forces: gravity, electromagnetism, and the strong and weak nuclear forces. This dark radiation does not fit neatly into any of these categories. It behaves like a force carrier, something that transmits energy, but it's a carrier for which we have no particle and no theory. The hunt for an explanation leads us into some of the most speculative and thrilling realms of theoretical physics. One compelling idea involves the hypothetical action. This light, ghostly particle was originally proposed to solve a problem in particle physics, and it is a prime candidate for dark matter. But certain theories suggest that actions could also decay into photons under the influence of strong magnetic fields. What if the reverse is happening here? What if photons' ordinary light are being converted into actions or a similar weakly interacting particle within these specific regions? This process would effectively make the light disappear from our view, transforming into a form of dark radiation that can travel unimpeded through space, only to reconvert back into detectable energy when it interacts with matter in just the right way, depositing heat and causing the strange chemical changes we observe. In this scenario, the dark radiation sources are not emitters but transformers, acting as cosmic way stations that change one type of energy into another. An even more profound possibility is that we are seeing the direct influence of a hidden sector of particles and forces. This is the concept of a shadow universe, a complete set of particles and forces that parallel our own but only interact with our matter through gravity. And perhaps, as this discovery suggests, through this new, faint dark radiation channel. In this shadow sector, there could be their own version of stars, their own energetic processes, their own laws of physics playing out right alongside us. The dark radiation we detect could be the faint, leaked energy from a supernova explosion in that parallel reality, or the steady output of a shadow star, finally making its presence known not by its light, but by its subtle and mysterious heating effect on our own galactic gas. If true, this would mean we are not just mapping a single galaxy, but are inadvertently peering into the workings of an entire other cosmos, forever invisible yet forever intertwined with our own through these strange and energetic whispers. The breathtaking complexity of this galaxy continues to unfold as we venture into one of its most mystifying and conceptually challenging phenomena. Woven throughout the spiral arms of NGC 1300, astronomers have mapped a pattern so intricate and vast that it defies simple astronomical explanation. This is not a structure of gas and dust, but a pattern of connection. Vast webs of recently formed star clusters are linked by faint but detectable pathways of highly specific cosmic ray emissions, creating a filamentary network that bears a stunning, and some would say unsettling, resemblance to a biological neural network. It's as if the galaxy itself has grown a brain, with brilliant young stars acting as firing neurons and the streams of energetic particles between them serving as synaptic connections. The scale of this structure is nearly incomprehensible. The neurons, which are massive clusters of hot blue stars, are separated by hundreds of light years. The axons linking them are not physical wires but corridors of space where a consistent, low-frequency flux of cosmic rays and other high-energy particles can be detected, creating bridges of energy between the stellar nodes. When this immense web is visualized in three-dimensional models, the comparison to the neural architecture of a biological brain is not merely poetic, it is visually uncanny. The pattern follows the same principles of efficient connectivity found in complex networks everywhere, from the human cerebral cortex to the internet, suggesting a universal law of organization is at work, one that operates on scales from the microscopic to the galactic. This discovery ignites a fierce debate that straddles the line between rigorous science and profound philosophy. The orthodox conservative view dismisses the resemblance as a spectacular example of pareidolia, the human tendency to see familiar patterns in random data. From this perspective, we are simply connecting the dots of a natural, self-organizing structure and imposing our own biological blueprint upon it. The network, they argue, is likely the result of well-understood, if complex, astrophysical processes. Shock waves from supernova could trigger star formation in a chain reaction, while the galaxy's magnetic fields might channel cosmic rays into coherent streams, creating the illusion of designed connections through purely physical means. Yet, a growing number of interdisciplinary thinkers, drawing from fields like neurobiology, complexity theory, and systems philosophy, propose a far more radical interpretation. They point to the fact that the same mathematical principles that govern network efficiency, such as small world design and scaling laws, appear to govern both the human brain and this cosmic structure. This, they argue, is more than mere coincidence. It could be a fundamental signature of how information and complexity organize themselves in the universe. In this view, consciousness might not be an isolated accident confined to wetware inside skulls on planets. Instead, it could be an emergent property of any sufficiently complex, interconnected system. A galaxy, with its billions of stars and intricate feedback loops of energy and matter, could possess a level of complexity that allows for a form of nascent, cosmic-scale consciousness, a slow, vast, and utterly alien form of thought operating over millions of years. This idea, often called the cosmopsychism hypothesis, suggests that what we perceive as a mindless universe might actually be a deeply mindful one, and that our own individual consciousnesses are not separate from it, but rather localized expressions of this fundamental cosmic mind. The neural network in NGC 1300 would then be a physical manifestation of this process, a glimpse into the underlying connective fabric of a sentient cosmos. Whether this is a literal truth or simply a beautiful metaphor for the universe's inherent order, the cosmic consciousness network challenges us to expand our definition of life, intelligence, and mind itself, inviting us to consider that the greatest mysteries of existence may be written not in the language of physics alone, but in the pattern of connections that bind all things together. And now we arrive at a discovery that strikes at the very heart of quantum theory's most fundamental and bizarre principle, probability. Scattered throughout the arms of NGC 1300 are regions that researchers have cautiously labeled probability manipulation zones. These are not places where strange objects are found, but rather pockets of space where the foundational rules of chance themselves appear to be broken. For decades, the core of quantum mechanics has been its inherent randomness. When you measure a property of a particle, like its spin, the outcome is not predetermined. It is governed by a cloud of probability. All we can ever know are the odds. In these zones, however, those odds are being rigged. The universe's cosmic dice are coming up loaded. the evidence comes from a series of remarkably simple, yet profoundly unsettling, experiments conducted by observing the light from distant quasars as it passes through these regions. This light is polarized, meaning its waves oscillate in a specific direction. As it journeys for billions of years, individual photons in that light beam can interact with the quantum foam of empty space in a way that subtly rotates their angle of polarization. This is a well-understood quantum effect, and crucially, it is a perfectly random process for each individual photon. When this light finally arrives at our telescopes, physicists can analyze the polarization angles of millions of these photons. According to every established law of quantum mechanics, the distribution of these angles should form a perfect, smooth bell curve, a Gaussian distribution. This is the unmistakable fingerprint of true, unbiased randomness, but in the light that has traveled through these specific zones, that fingerprint is smudged. The distribution of polarization angles is skewed. It's lopsided. Instead of a smooth curve, the data shows sharp peaks and strange, repeating patterns within the statistical noise. It's as if someone took the results of flipping a fair coin 1,000,000 times and found not a roughly even split of heads and tails, but a clear, precise pattern like heads, tails, tails, heads, repeating in a sequence that defies chance. The probability of this happening naturally is so astronomically low that it points to only one conclusion. Some influence within these zones is actively tampering with quantum probabilities on a scale of light years. The randomness is being suppressed, guided, or overwritten. The implications of this are almost too large to grasp. If quantum probabilities are not truly random but can be influenced, it means that the universe at its most fundamental level may not be governed by chance alone. There could be a hidden variable, a currently unknown force or factor that biases quantum outcomes. This was the dream of Einstein, who famously rejected pure randomness, stating that God does not play dice with the universe. He believed in a deeper, deterministic reality hidden beneath the quantum veil. The data from these zones suggests he might have been onto something, though the mechanism would be far stranger than anything he imagined. So what could possibly be strong enough to bend the rules of probability across such vast distances? One compelling theory returns to the idea of the quantum vacuum. We know that empty space is not empty, it is a dynamic sea of energy. In these zones, the energy of this vacuum could be in an exotic state, creating a field that interacts with passing particles and subtly biases their quantum choices. It would be like rolling dice on a table that is not level. The outcome is no longer fair. The field wouldn't force a specific result every time, but it would gently nudge the probabilities, making some outcomes vastly more likely than others. An even more mind-bending possibility involves the non-local nature of quantum mechanics itself. The phenomenon of entanglement shows that particles can be instantaneously connected across vast distances. What if the particles within one of these zones are not just entangled in pairs, but are part of a galaxy-wide, interconnected quantum network? In such a massively entangled system, the act of measuring one particle could have a ripple effect that biases the probabilistic outcomes of countless other particles across the entire region, creating a coordinated, non-random pattern that emerges from the collective whole. The zone wouldn't be manipulating probability from the outside. It would be a single, vast quantum system where probability itself is a shared property. This discovery forces us to confront a truly profound question. Is randomness truly a fundamental property of nature, or is it merely a placeholder for a deeper law we have not yet discovered? The probability manipulation zones of NGC 1300 suggest that the answer may be written in the stars, hidden in the subtle, non-random flicker of light that has traveled across the cosmos to tell us that the game is not what we thought it was. We now turn our attention to a concept so abstract it challenges the very nature of reality and time. If the quantum gravity signature showed us the pixelated grain of spacetime, then this next phenomenon suggests those pixels can hold a picture. In specific, calm regions of NGC 1300, gravitational wave astronomers have detected something that should not exist: faint, precise echoes of massive cosmic events that occurred millions of years ago. It's as if the void itself has not forgotten the violence that once tore through it, and under the right conditions, it can play that memory back for those who know how to listen. This discovery began with the meticulous analysis of data from the most advanced gravitational wave observatories. After a significant event like the merger of two black holes, the detectors record the primary signal, the famous chirp as the objects spiral inward and collide. According to our standard models, that signal should then ring down and fade into silence as the new, larger black hole settles into a calm state. But for events whose waves pass through certain sectors of NGC 1300, that isn't the end of the story. Long after the main event has passed, the detectors pick up a series of faint, repeating after vibrations. These are not random noise, they are a perfect, albeit quieter, replication of the original collision signal. It's the cosmic equivalent of shouting into a canyon and hearing your own voice return to you moments later, a clear echo. But in the vacuum of space, there are no canyon walls. There is nothing for the gravitational waves to bounce off of. So what are they echoing from? The leading theory is as revolutionary as it is bizarre. It proposes that spacetime is not a passive stage upon which events unfold, but an active participant with properties we are only beginning to understand. Specifically, that it might possess a form of memory, in the same way that a piece of iron can be permanently magnetized, or a glass vase can shatter and retain the stress patterns of its breakage. Spacetime may be capable of being permanently imprinted by immensely energetic events. The violent curvature and twisting caused by a black hole merger could alter the very fabric of spacetime in a persistent way, leaving behind a kind of fossilized strain or a topological scar. This scar wouldn't dissipate, it would become a permanent feature of that region. Then, when subsequent gravitational waves from other events pass through this scarred region, they interact with this fossilized strain. The memory of the past event is imprinted onto the new waves, creating a faint echo that arrives at our detectors out of sync with the original signal. This idea finds support in some of the most advanced theoretical work in physics, particularly in the concept of soft gravitons. These are hypothetical, very low energy particles that are theorized to be emitted in countless numbers during any gravitational event. According to this line of thinking, these soft gravitons don't just fly off into the void. They linger, settling into the background structure of space-time and subtly altering its properties. A region that has witnessed many such catastrophic events would be saturated with these particles, effectively encoding a history of violence into its fundamental geometry. This region would then act as a kind of gravitational prism, bending and coloring any new waves that pass through it, making them carry the information of events long past. The implications of spacetime with memory are staggering. It suggests the universe might naturally keep a perfect, immutable record of everything that has ever happened. Every supernova, every collision, every birth of a black hole could be permanently written into the fabric of reality. If we could learn to read this memory, we wouldn't need to just look at the light from the past. We could literally feel the gravitational vibrations from the dawn of time. We could witness the very first black hole mergers, not by their faint, redshifted light, but by the direct echo of their catastrophic energy, preserved for billions of years in the spacetime of galaxies like NGC 1300. This isn't just a new way to observe the cosmos, it is a potential gateway to the ultimate history book, a chronicle of creation written in the language of gravity itself, waiting in the silence to be read. And now we come to a discovery so foundational it questions the very rulebook of the universe. For centuries, physics has been built upon a bedrock of unchanging truths, the fundamental constants. These are the fixed numbers that dictate the strength of forces, the speed of causality, and the very scale of reality itself. The fine structure constant governs the strength of electromagnetism. The speed of light in a vacuum is the universe's ultimate speed limit. Planck's constant sets the scale of the quantum world. These values are believed to be, as their name implies, constant, the same everywhere and everyone in the cosmos. They are the inviolable settings of our simulation, but meticulous observations within NGC 1300 suggest that in this distant island of stars, the settings might be slightly different. This isn't a finding that leaps out at you. It requires painstaking, precise work, comparing the faint light from this galaxy to the most exact laboratory measurements we have on Earth. The method relies on spectroscopy, splitting the light from distant atoms into its constituent colors to create a unique barcode. Each element has a specific pattern of lines at specific frequencies. The key is that the precise spacing and position of these spectral lines are exquisitely sensitive to the values of the fundamental constants. If, for example, the fine structure constant were slightly larger in NGC 1300, the lines in its cosmic barcode would be subtly shifted compared to the barcode we create in labs on Earth. After years of collecting and analyzing this faint starlight, that is precisely what researchers believe they have found. The shifts are tiny, a few parts in a million, but they are consistent and they are statistically significant. The universal constants, the most reliable things in existence, appear to be inconstant. The immediate knee-jerk reaction from any physicist is to question the instruments or the interpretation. Perhaps there is an unknown systematic error, some strange interaction of the light with the interstellar medium of NGC 1300 that mimics the signature of a changing constant. But as those possibilities are systematically ruled out, a far more thrilling and terrifying prospect emerges. The laws of physics might not be universal. They could be more like local ordinances, varying from one galactic province to another. Imagine the implications, the strength of the forces that hold atoms together, the energy levels that allow chemistry to happen, the very speed of light. All of these could be variables set during the birth of a galaxy. Life as we know it is exquisitely tuned to our specific set of constants. If the strength of the nuclear force were a fraction of a percent different, stars might not burn or the elements necessary for life might never be forged. The discovery of variation suggests that our universe might not be a single, monolithic entity with one set of rules, but a patchwork quilt of domains, each with its own slightly different physics. In some regions, the constants might allow for chemistry and life as we know it. In others, with different values, the universe could be a barren, inert void, or a realm of such ferocious energy and rapid reactions that complexity could never arise. This concept, known as the multiverse or the anthropic principle, moves from philosophical speculation into the realm of testable science if we can confirm that the rules are indeed different elsewhere. What could cause such a fundamental variation? One of the most compelling explanations emerges from string theory, which proposes that the fundamental constants are not truly fundamental. Instead, they might be the result of how the extra, tiny dimensions predicted by the theory are shaped and folded, a concept known as compactification. The specific geometry of these dimensions dictates the values we measure in our four-dimensional spacetime. In this view, our universe underwent a specific dimensional folding that locked in our particular set of constants. But what if that process wasn't uniform? The early universe might have cooled and settled into different vacuum states in different regions, like water freezing into ice with slightly different crystal orientations in different parts of a pond. Each of these regions would have its own unique dimensional geometry, and therefore its own unique values for the constants of nature. NGC 1300 could be residing inside one of these bubbles, a domain where the hidden dimensions are folded in a slightly different way, giving it a subtly different version of physical law. We are not just looking at a galaxy. We could be looking into a separate branch of the multiverse, a neighboring reality with its own rules, located unimaginably far away, yet right there in our telescopes. The tiny shifts in a light spectrum are then not mere measurement anomalies. They are our first glimpse into the infinite variability of existence itself. After journeying through 29 profound mysteries that twist the laws of physics and redefine reality itself, we arrive at the final and perhaps most mind-expanding possibility of all, a concept that draws every one of these strange threads into a single, breathtaking tapestry. The accumulated anomalies of NGC 1300 present a picture so deeply strange, so consistently irrational from the viewpoint of standard physics, that a small but growing number of scientists and philosophers are daring to ask a question that was once confined to science fiction. Are we looking at glitches in the code? Could the bizarre, rule-breaking behavior of this galaxy be the first tangible evidence that our universe is not a base reality, but an incredibly sophisticated simulation? This idea, known as the simulation hypothesis, is not as outlandish as it might first sound. The core argument is based on a simple projection of technological advancement. If any civilization, anywhere, ever reaches a level of computing power vast enough to simulate a universe, even a universe of conscious beings, then the number of simulated realities would quickly dwarf the one single original reality. Statistically, therefore, we are more likely to be living in one of those countless simulations than in the original base reality. It's a modern, technological twist on an ancient philosophical puzzle. When viewed through this lens, the phenomena within NGC 1300 stop being mere anomalies and start looking like potential artifacts of a computational process. Take the quantum star cluster, where stars exist in superimposed states until observed. This mirrors a common optimization technique in computing known as lazy evaluation, where the precise state of an object isn't calculated until it is absolutely needed by another process, saving immense processing power. The system doesn't render a star's definitive state until a conscious observer, a user within the simulation, looks directly at it. Consider the information horizon, a spherical region from which no data can escape. This is the perfect analog of a rendering boundary in a video game, where the program only generates detailed environments for the area a player is currently in. Anything outside that bubble isn't processed in full detail to conserve resources. The horizon could be a literal draw distance setting for that sector of the galaxy, a limit placed on how much of the simulation is fully computed at any given time. The probability manipulation zones, where quantum randomness breaks down into predictable patterns, could be evidence of a random number generator that isn't perfectly random. In even the best simulations, pseudorandom number generators can develop biases or repeat patterns over vast scales, a potential flaw we might be detecting in the very fabric of spacetime. Similarly, the gravity lens paradox and the strange behavior of the phantom spiral arm could be interpreted as signs of a simplified physics engine. Instead of calculating the impossibly complex gravitational interactions for every single star, the simulation might use an approximation, a statistical model of dark matter, that occasionally produces errors or inconsistencies, which we detect as gravitational anomalies that don't match the visible mass. Even the most jarring phenomena find a chillingly logical explanation. The chronodistortion nebulae, where the past and present coexist, could be a case of latency or caching issues, where data from different points in the simulation's process are accidentally being displayed together. The silent supernovae, which lack their expected neutrino and gravitational wave signals, might be a case of the simulation cutting corners on processing extremely high-energy, short-duration events, rendering only the visual flash but skipping the more computationally expensive physics calculations. Of course, the scientific community approaches this idea with immense skepticism, as it should. The primary counter-argument is a modern take on Occam's razor. it is far simpler to assume that we simply don't yet understand the new physics at work in NGC 1300 than to assume an entire universe-sized simulation run by unknown beings. These anomalies are not proof of a simulation. They are puzzles that challenge us to expand our knowledge, to discover new particles, new forces, and new principles that operate on galactic scales. They are a call to do better science, not to default to a metaphysical explanation. Yet, the simulation hypothesis remains a powerful and provocative framework. It forces a profound shift in perspective. If there is even a remote possibility that we are in a simulation, then the goal of science changes. We are no longer just uncovering the laws of nature. We are reverse engineering the source code of reality itself. Every strange phenomenon, every broken law, becomes a potential clue to the architecture of the simulation, the language it was written in, and perhaps even the intentions of its creators. NGC 1300, in its glorious and bewildering complexity, doesn't give us the answer, but it presents us with the most compelling crime scene, littered with evidence that points toward a truth so vast our minds can scarcely comprehend it. The investigation is just beginning. From the profound silence at its heart to the intricate cosmic web that hints at a form of galaxy-wide consciousness, NGC 1300 has proven to be far more than a simple collection of stars. It is a living laboratory of the impossibly strange, a place where the universe seems to be running experiments on itself, bending and breaking the very rules we believed were set in stone. Each of these 30 phenomena, from the spacetime memory and the inconstant constants to the probability manipulation zones and the haunting simulation hypothesis, represents a fundamental challenge. They are not mere puzzles to be solved with bigger telescopes. They are direct confrontations with our most deeply held beliefs about how reality operates. This single galaxy, a tiny island in the vast cosmic ocean, has become the central front in our quest to understand everything, forcing us to question the nature of gravity, time, information, and even our own consciousness. What does this incredible diversity of mystery ultimately reveal? It shows us that the universe is far richer, far more complex, and far more mysterious than we ever dared imagine from our small corner of it. For centuries, we have looked up at the night sky and seen a clockwork universe, predictable and governed by immutable laws. But NGC 1300 presents a different vision, a universe that is dynamic, participatory, and perhaps even computational. These anomalies suggest that reality might not be a single, monolithic entity, but a tapestry woven from many different threads of physical law, where the constants are not constant and the past is not even past. They invite us to consider that what we call physics might merely be the local customs of our particular cosmic neighborhood, and that over the horizon of the known, entirely new chapters of science are waiting to be written. This journey through the unknown doesn't end here, it's really just the beginning. Every one of these mysteries is an open door, an invitation to explore, to question, and to wonder. So now we turn it over to you. Which of these 30 strange phenomena captured your imagination the most? Was it the ghostly silence of the radio void, the impossible resurrection of ancient stars, or the spine-tingling possibility that we might be living in a simulation whose code is showing through? Share your thoughts and your favorite cosmic mystery in the comments below, and let's continue this conversation about the greatest wonders